Welcome to this coding session. Today, we'll be exploring LeetCode problem number 611, valid triangle number. This problem is a great exercise in understanding and applying array manipulation techniques to solve real-world geometric constraints. Let's dive in and learn how to approach this step by step. In this problem, we're tasked with determining how many valid triangles can be formed from a given array of integers, where each integer represents a potential side length of a triangle. To form a valid triangle, the three sides must satisfy the triangle inequality. This means that the sum of any two sides must be greater than the third side. Specifically, for a triplet, nums I, nums j, nums k, the following conditions must hold: nums I plus nums j, nums k, nums I plus nums k, nums j, and nums j plus nums k, nums I. The input to this problem is an array of integers, and the output is an integer indicating the number of valid triplets that meet these conditions. The goal is to count all such valid triplets in the array. Let's look at an example to understand this better. Suppose the input array is nums equals 2, 2, 3, 4. The output for this input is 3 because there are 3 valid triplets that satisfy the triangle inequality. The valid triplets are 2, 3, 4, 2, 3, 4, again, and 2, 2, 3. Notice that duplicate numbers in the array can lead to repeated but valid triplets, and all of them are included in the count. This highlights the importance of checking all possible combinations to ensure we don't miss any valid triangles. Now, let's take a look at another example. In this next example, the input array is nums equals 4, 2, 3. Here, the output is 0, which means no valid triplets can be formed. This happens because no combination of three numbers in the array satisfies the triangle inequality conditions. This example helps us see that the triangle inequality is a strict requirement, and if it's not met, the triplet cannot form a valid triangle. Beyond examples, we also need to consider constraints and edge cases for this problem. The constraints for this problem are as follows. The length of the array can range from 1 to 1000, and each element in the array can range from 0 to 1000. Key edge cases include arrays with fewer than 3 elements, which will always result in 0 because a triangle requires at least 3 sides. Similarly, if all elements are 0, no valid triangle can be formed. Duplicate values in the array must be handled carefully to ensure all unique valid triplets are counted. A key observation is that the triangle inequality condition is central to solving this problem. By sorting the array, we can simplify the conditions to just checking if the sum of two smaller sides is greater than the largest side. Sorting also opens the door to more efficient algorithms, reducing the time complexity to n squared, by leveraging the ordered structure of the array. This optimization is crucial for handling larger input sizes within the given constraints. To solve the valid triangle number problem, we need to count all the valid triplets in the array that satisfy the triangle inequality. The brute force approach involves checking every possible triplet using 3 nested loops. For each combination of indices I, j, and k, we verify if the sum of the two smaller sides is greater than the largest side. While this method is simple to understand, it has a time complexity of n cubed, which makes it impractical for larger input sizes. To optimize this, we consider a more efficient approach that involves sorting the array. By sorting the array in ascending order, we can simplify the triangle inequality check, as the condition can now be evaluated more systematically. In this optimized method, the largest side of the triangle, nums k, is fixed using a loop, and we use 2 pointers to efficiently find pairs that satisfy the condition. This reduces the computational cost significantly compared to brute force. After sorting the array, we fix the largest side, nums k, and use 2 pointers to identify pairs of smaller elements. If the sum of nums I and nums j satisfies the inequality, then all pairs between these indices are also valid because the array is sorted. This property eliminates the need to explicitly check each pair, making the process more efficient. The time complexity of this approach is n squared, where sorting takes n log n, and the 2-pointer technique processes all pairs in n squared. Additionally, the space complexity is constant, 1. Another alternative is to use binary search after sorting. For each pair of indices I and k, we can use binary search to locate the largest valid index j such that the sum of nums I and nums j is greater than nums k. While this approach is also valid, its time complexity is O, n squared log n, due to the additional logarithmic cost of binary search, making it slightly slower than the two-pointer technique. This is why the two-pointer method is generally preferred for its simplicity and speed. The chosen strategy for this problem is the optimized approach using sorting in two pointers. It strikes a balance between efficiency and simplicity. Sorting the array ensures that smaller sides come before larger sides, which simplifies the triangle inequality check. The two-pointer method then efficiently counts valid pairs without requiring additional overhead, achieving an O, n squared solution. One key insight is that once the triangle inequality is satisfied for a pair of indices, it will hold for all combinations of indices between the two pointers. This eliminates redundant checks and leverages the sorted order effectively. In comparison, brute force is too slow due to its cubic complexity, and while binary search is a valid alternative, it introduces a logarithmic overhead, making it slightly less efficient. Overall, the two-pointer approach is the most practical choice, as it provides the best trade-off between computational performance and ease of implementation. In this problem, we need to determine how many triplets in the array can form a valid triangle based on the triangle inequality condition, which states that the sum of any two sides must be greater than the third side. Specifically, we are looking for triplets where the indices satisfy the condition I less than j less than k. To solve this problem efficiently, we use a two-pointer approach combined with sorting the array. Sorting is an essential first step because it allows us to simplify the problem. Once sorted, if nums I and nums j are two sides, their sum will always be the smallest possible for those indices. This guarantees that we only need to check whether the sum of these two sides is greater than the third side, nums k. Sorting the array takes O, n log n, time, and it simplifies subsequent operations by ensuring the elements are in ascending order, which is critical for the triangle inequality check. After sorting, we iterate through the array in reverse, considering each element as the potential longest side of the triangle. Let k represent the index of this largest side, nums k. By fixing the largest side first, we narrow our focus to finding two smaller sides, nums I and nums j, such that their sum exceeds nums k. To officially find these pairs, we use two pointers, one starting at the beginning of the array, I equals 0, and the other just before the largest side, j equals k1. The two-pointer technique simplifies the process of identifying valid pairs. While I is less than j, we check if nums I plus nums j is greater than nums k. If this condition is true, it means all pairs between I and j are valid with nums k, because the array is sorted. We then add the count of these pairs, which is j I, to our result. After this, we move the right pointer, j, one step to the left to consider smaller pairs. This ensures we systematically evaluate all valid combinations for the current largest side. On the other hand, if nums I plus nums j is not greater than nums k, it means the current pair does not satisfy the triangle inequality. To address this, we move the left pointer, I, one step to the right to increase the sum and recheck the condition. This process continues until the two pointers meet. The key insight here is that the two-pointer approach allows us to efficiently evaluate all valid pairs without resorting to a brute force method, which would involve nested loops and significantly higher time complexity. By repeating this process for every possible k, we accumulate the total count of valid triangles. Sorting the array at the beginning is critical to make this approach work, as it ensures the elements are in an order that facilitates the triangle inequality check. Additionally, by moving the pointer strategically, we avoid redundant calculations and ensure that each pair is evaluated exactly once. This significantly optimizes the algorithm compared to a naive approach. For this algorithm, the input array nums is sorted in place, so no additional data structures are required. We only use a single integer counter to track the number of valid triangles, making the space complexity O1. In terms of time complexity, sorting the array takes O, n log n, and the two-pointer traversal for each k runs in O, n, time in the worst case. Since we iterate over all k values, the total time complexity is O, n squared. This is a significant improvement over the O, n cubed, complexity of a brute force approach. There are also some important edge cases to consider. If the input array has fewer than 3 elements, no triangles can be formed, so we should immediately return 0. If the array contains values such that the two largest elements do not satisfy the triangle inequality, no valid triangles exist. Duplicates are acceptable as long as they satisfy the triangle condition. Negative or zero values do not need special handling if the input guarantees positive integers, as they are inherently invalid for triangle sides. Let's walk through an example with the input array nums equals 2, 2, 3, 4. First, we sort the array, resulting in 2, 2, 3, 4. We begin by selecting the largest side, nums, k, starting with k equals 3, where nums, k, equals 4. We initialize I equals 0 and j equals 2. Using the two-pointer approach, we check if nums, I, plus nums, j, nums, k, or 2 plus 3 greater than 4. Since this condition is true, it means the pairs, nums, 0, nums, 2, and nums, 1, nums, 2, are valid with nums, k. We add ji, which is 2, to our count and move the right pointer, j, to 1. We then check the condition again, nums, I, plus nums, j, or 2 plus 2 greater than 4. This time it's false, so we move the left pointer, I, to 1. The pointers meet, so we stop for this k. We then repeat the process for k equals 2 and k equals 1, adding valid pairs to the count. Ultimately, the total number of valid triangles is 3. This solution addresses LeetCode problem number 611, valid triangle number, using a combination of sorting and the two-pointer technique to efficiently count valid triangles. Explanation. 1. Sorting the array. The first step is to sort the input array nums. This simplifies the triangle inequality check because if nums, k, is the largest side, then the other two sides nums, I, and nums, j, only need to satisfy nums, I, plus nums, j, nums, k. 2. Outer loop. Choosing the largest side, the loop iterates through the array, starting from the third element, index 2. This is because a triangle requires 3 sides, and nums, k, is treated as the largest side. 3. Two-pointer technique. For every k, initialize 2 pointers, I, starting at the smallest side, and j, just before k. Use the two-pointer approach to efficiently count pairs, nums, I, nums, j, that satisfy the triangle condition. 4. A triangle inequality check. If nums, I, plus nums, j, nums, k, all pairs between I and j are valid because the array is sorted. Add ji to the count and move the j pointer leftward to explore the next smaller side. Otherwise, increment I to test the next larger side. 5. Returning the result. After iterating through all possible values of k, return the total count of valid triangles. Complexity. Sorting the array takes O, n log n. Two-pointer traversal. For each k, the two-pointer scan is O, n, in the worst case. Since k iterates up to n, the overall complexity is O, n squared. This approach is efficient and handles edge cases like small arrays, less than 3 elements, by returning 0, as no triangles can be formed. The use of sorting in 2 pointers ensures that the solution is both optimal and easy to understand. This is the Java implementation of LeetCode problem number 611, valid triangle number. The logic mirrors the provided Python solution, using a 2-pointer approach after sorting the array. Java-specific differences include explicit type declarations, use of arrays.sort for sorting, and the standard Java class structure. The implementation iterates through the input array and counts valid triangle combinations efficiently. To solve the problem, we start by sorting the input array, which gives us nums equals 2, 2, 3, 4. Sorting helps us efficiently check the triangle inequality condition using 2 pointers. Next, we initialize 2 variables, n to store the length of the array, which is 4 in this case, and count, which starts at 0 and will track the total number of valid triangles we find. Now, we iterate through the array and treat nums, k, as the largest side of a potential triangle. For the first iteration, where k equals 2, the largest side is 3. We initialize 2 pointers, I equals 0 and j equals 1, representing the other 2 sides. We check if nums, I, plus nums, j, nums, k, or 2 plus 2 3. Since this condition is true, we know all pairs between I and j form valid triangles. Here, there is only one such pair, so we add ji, which is 1, to our count. After this, we decrement j to 0, and since I is no longer less than j, we exit the while loop. At the end of this iteration, the total count of valid triangles is 1. For the second iteration, we set k equals 3, making for the largest side. The left pointer I is set to 0, and the right pointer j is 2. First, we check if nums I plus nums j nums k or 2 plus 3 4. This condition is true, so we add ji, which is 2, to our count. We then decrement j to 1 and check again nums I plus nums j nums k or 2 plus 2 4. This time, the condition is false, so we increment I to 1. At this point, I is no longer less than j, so we exit the while loop. The total count of valid triangles for this example is now 3. This is our final output for this input array. In the second example, the input array nums equals 4, 2, 3, 1 is first sorted, giving us nums equals 1, 2, 3, 4. We initialize n as 4 and count as 0. We then begin iterating through the array. For the first iteration, where k equals 2, the largest side is 3. The left pointer I is set to 0, and the right pointer j is 1. We check if nums I plus nums j nums k or 1 plus 2 3. This condition is false, so we increment I to 1. At this point, I is no longer less than j, so we exit the while loop. At the end of this iteration, the total count of valid triangles remains 0. For the second iteration in this example, k equals 3, making for the largest side. The left pointer I is set to 0, and the right pointer j is 2. First, we check if nums I plus nums j nums k or 1 plus 3 4. This condition is false, so we increment I to 1. Now we check again nums I plus nums j nums k or 2 plus 3 4. This time, the condition is true, so we add ji, which is 1, to our count. We then decrement j to 1. At this point, I is no longer less than j, so we exit the while loop. The total count of valid triangles for this example is now 1. This is our final output for this input array. In the third example, the input array nums equals 2, 2, 2, 2 is already sorted as nums equals 2, 2, 2, 2. We initialize n as 4 and count as 0. For the first iteration, where k equals 2, the largest side is 2. The left pointer I is set to 0, and the right pointer j is 1. We check if nums I plus nums j nums k or 2 plus 2 2. This condition is true, so we add ji, which is 1, to our count. We then decrement j to 0. Since I is no longer less than j, we exit the while loop. At the end of this iteration, the total count of valid triangles is 1. For the second iteration in this example, k equals 3, making 2 the largest side. The left pointer I is set to 0, and the right pointer j is 2. First, we check if nums I plus nums j nums k or 2 plus 2 2. This condition is true, so we add ji, which is 2, to our count. We then decrement j to 1 and check again nums I plus nums j nums k or 2 plus 2 2. This condition is still true, so we add ji, which is 1, to our count. We then decrement j to 0. At this point, I is no longer less than j, so we exit the while loop. The total count of valid triangles for this example is now 4. This is our final output for this input array. To analyze the time complexity of our algorithm, we start with the sorting step. Sorting the input array nums takes O, n log n, time, where n is the size of the array. Once the array is sorted, the main work happens in a nested loop structure. The outer loop iterates from index k equals 2 to n1, which means it runs O, n, times. Inside this outer loop, we employ a two-pointer approach with pointers I starting at 0 and j starting at k1. The inner while loop continues as long as I less than j, processing the subarray nums, 0 k. In the worst case, the inner loop runs O, k, iterations for a given k, since j decreases as I increases. To determine the total work done by the inner loop across all iterations of the outer loop, we sum up the lengths of the subarrays processed by the two-pointer approach. This sum evaluates to 1 plus 2 plus 3 plus n2, which simplifies to n2, n1/2, or O, n squared. Bringing these components together, the overall time complexity consists of two parts, sorting, which is O, n log n, and the two-pointer approach, which contributes O, n squared. Since O, n squared, dominates O, n log n, the total time complexity of the algorithm is O, n squared. Now, looking at space complexity, the algorithm sorts the input array in place, meaning no additional space is required for the sorting step. The only additional memory used is for a constant number of auxiliary variables like n, count, I, j, and k. This means the space complexity of the algorithm is O(1), as it does not depend on the size of the input array and operates entirely in place. To appreciate the efficiency of this approach, it helps to compare it against the brute force method. A naive solution would involve checking all possible triplets, nums, I, nums, j, nums, k, using 3 nested loops, leading to a time complexity of O, n cubed. The current algorithm is a significant improvement because sorting the array allows us to focus only on valid candidates for the largest side of the triangle. The two-pointer approach eliminates the need to explicitly check all combinations, which reduces redundancy and brings the complexity down to O, n squared. In terms of best, average, and worst-case scenarios, the best case occurs when the inner while loop can terminate early, such as with small or highly constrained inputs. However, the overall complexity is still dominated by O, n squared. In the average and worst cases, where inputs are larger and more diverse, the inner loop runs close to its maximum iterations, and the complexity remains O, n squared. The quadratic term arises because the lengths of subarrays processed by the two-pointer approach grow as the square of the input size, while the sorting step contributes a smaller O, n log n, term. This is why the final time complexity is O, n squared. When tackling this problem, there are a few common mistakes to watch out for. First, forgetting to sort the array is a frequent error. Sorting is essential because it allows us to use the two-pointer approach efficiently and ensures that the triangle inequality holds true. Without sorting, the order of the elements is unpredictable, which can lead to incorrect results. Another mistake is how the two-pointer approach is implemented. Instead of resetting both pointers for every new iteration of the outer loop, you should adjust only the k-pointer dynamically while keeping j fixed. This avoids unnecessary computations and keeps the solution efficient. Additionally, some solutions mistakenly allow overlapping indices, such as I equals j, j equals k, or I equals k. This violates the constraint that I less than j less than k, so it's important to enforce this properly. Lastly, in languages like Java or C++, integer overflow can occur when summing large values, leading to incorrect results. Be mindful of this and use techniques like typecasting or boundary checks to prevent it. Another common variation is inefficient brute force implementations. A naive O, n cubed, solution, where every triplet is checked manually, might work for small arrays but will time out for larger inputs. Instead, optimizing the solution to O, n squared, using sorting and the two-pointer technique is crucial for handling larger test cases efficiently. Now, from an interview perspective, there are some key insights to keep in mind. First, sorting the array simplifies the problem significantly because the triangle inequality can then be reduced to checking whether the sum of two sides is greater than the third. The two-pointer approach, when combined with sorting, allows you to fix one side of the triangle and efficiently count valid combinations for the other two sides, reducing time complexity. Always consider edge cases like an empty array, very small arrays, or arrays with duplicate values. Finally, in an interview, it's important to explain your trade-offs clearly. Highlight why sorting is necessary and how the two-pointer approach balances efficiency and correctness. This problem shares similarities with other well-known LeetCode problems that also involve triplets. For example, in LeetCode 15, the three-sum problem, sorting and two pointers are used to find triplets that sum to 0. In LeetCode 16, the three-sum closest problem, the idea is to identify triplets that come closest to a specific target. LeetCode 18, or the four-sum problem, extends this pattern further by finding quadruplets, while LeetCode 259, the three-sum smaller problem, involves counting triplets that satisfy a specific sum constraint. Each of these problems builds on the same foundational techniques. As for alternative approaches, brute force is the simplest but least efficient option, with O, n cubed, complexity. Binary search can also be used after sorting, where you iterate through pairs and find the largest valid k using a binary search. This has a complexity of O, n squared asterisk log n, making it slower than the two-pointer method. Hashing, while useful in other contexts, is rarely applied here due to the difficulty of enforcing the I less than j less than k constraint efficiently. When choosing between different approaches, it's important to weigh their trade-offs. The two-pointer method is generally preferred because of its O(n)² complexity and straightforward implementation, making it both faster and simpler to code. Binary search, on the other hand, while slightly slower at O(n)² log n, can be more intuitive for some developers who are familiar with searching techniques. Brute force, with its O(n)³ complexity, is useful as a learning tool or for very small arrays but becomes impractical for larger inputs, especially in competitive programming or interviews. Understanding these trade-offs allows you to choose the right approach for the problem at hand, balancing efficiency, clarity, and the specific constraints you're working with. Thank you for watching. To wrap up, we've covered the key steps to solving the valid triangle number problem. Remember, the triangle inequality and efficient use of sorting and two-pointer techniques are the backbone of this solution. Don't forget to practice similar problems to solidify your understanding. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!